Okay, let's start. So, what is filtration? Today's topic is about filtration and its characteristics and its different types of filtration. So, first, what is filtration? So, we'll show the video. So, you can see that from here particles are entering, and then in the network between of the filters, the particles are captured. And then from the back side, clean flow is coming out. This is kind of a sand filter. So you see that first they are getting mixed inside it, and all the sands that are heavy in weight, they are coming down. This is kind of a sand filter. What are the main driving forces of filtration? What are the main driving forces of filtration?
Ma'am, pressure gradient?
Yes. Pressure, there is pressure, gravitational force, pressure, then gravitational force, electric field force, centrifugal force, and concentration force or concentration gradient. So these are all the main driving forces of filtration.
Ma'am, the pressure gradient are used in reverse osmosis?
Yes, pressure gradient is used in reverse osmosis.
Thank you.
So one by one we'll see. So first one is the gravity filtration process. So this is a filtration industry where the different filtration tanks are there. So you can see that feed is going inside through this pump, and here filtration starts when water passes through the diffuser and contacts the media. You are seeing that water is coming, passing through the, and all the particles which are heavy in nature, they are settling down slowly. So now they are settling down. So this is the nozzle. Nozzle controls the working parameters.
ये गए आपके ये कम मिल रहे हैं आज बहुत कम मिले बारिश की वजह से खिल गए इसीलिए इसे खुले रखो सड़ेगा नहीं
So this is the gravity
ठीक है
filter or
चाय
gravity filter.
हाथ कर लेना
Next one is the plane and frame type filter. Here you can see these are plate, end frame, and plate. Solid from liquids, these are plates. This is the filtered plate. This is a series of plate and frame are stacked with a hydraulic closing and preset pressure. So now the feed is coming using it under pressure. It travels through the opening frame and sockets, and filter liquid passes through the filter. This is a drain pipe. Here from each plate the dust particles that forms a cake on the filter that is falling down. You can see here. So now the fluid is here. This is the plane and frame type filter. Next one is the leaf filter. So this is called a vertical pressure leaf filter. Here the slurry is pumped under pressure into a vessel. So you can see slurry is going under pressure into a vessel. This is the filter and the feed is coming under pressure. And it is fitted with a stack of vertical leaves that serve as a filter element. So you can see the vertical leaves, right? So the tank is full now. So after cleaning in the filter, the clean solution is collecting in another tank. So the leftover things are cleaned in this chamber and they are separated from the clean water. Okay, so this is the leaf filter. Last one is the rotary vacuum filter. So these are the parts of the rotary vacuum filter. This is the drum, this is the washer, this is the dry bed, and this is the vat. So in rotary drum filter, always the machine washer is moving, rotating. The exterior washing pipes. This is the discharge scraper. So how the basic process working principle rotary filter is shown here. Okay, this is the filter. Next is the what are the filter medium used in filtration? What are the filter medium used in filtration? So, as a filter medium, different types of membranes are used. Different types of membranes are used, such as filter cloth, filter screen, then common filter paper, thickened masses barrier, sand beads, oak beds, sand beds, oak beds, porous ceramic, porous metal. Anything can be used as the filter medium or filter membrane. What is the use of compressor in filter? What is the use of compressor in filter?
Normally,
The compressor is used to push the particle laden fluid through the filter medium. So there should be a pressure difference for which the feed solution should pass through the filter, right? So this pressure difference is created by the compressor. Next, what is shape of support frame in filtration? What is the shape of support frame in filtration? Yes, rectangular and scalar both. So, what is the
Rectangular.
shape is rectangular and scalar both. So both will be correct, square and rectangular. Next, wrapper is used for washing in filtration. Is it true or false? Wrapper is used for washing filter. Huh, it is true. Next,
True.
what is the membrane in filtration? What is the membrane in filtration? What is membrane in filtration? So here we'll show the membrane. So the cylinder moves, first the cylinder moves forward, pressure automatically achieved and maintained at 3000 psi. Then chamber feeding, that means solutions are fed into the chamber. And pressure from the slurry entering the chamber causes the solids to deposit on the cloth, forming a cake and liquid to pass via outlet. So the solid particles are forming cake on the filter and the liquid is flowing through the chamber. So this is the clean water is coming. This is the now the filter cake needs to be washed because to keep the membrane intact. So this is the membrane cleaning process. This is the clear water into the membrane plate is going. Membrane plate is swelling up by high pressure water compressed air. So this is the swelling of the membrane. Membrane plate squeezing starts, it declares the moisture content in cake. Now they are showing the cross-sectional view of the membrane plate working, how the membrane plate works. So cross-sectional means feed is coming in the horizontal direction and water is coming through the vertical direction. That is why it is cross-sectional flow. So this is the clean part. Mainly the membrane is the main part of the filtration. So it needs to be taken care of. Next. The degree of separation in membrane is based on what in filtration? The degree of separation is based on what in filtration? Yes, it is dependent on the membrane charge, pore size and porosity.
Pore size
Membrane
and
charge,
porosity.
membrane porosity and the size of the pore. Size of the pore. Next. So the classifications of membranes. So basically membranes are divided into two portions, solid membrane and liquid membrane. This is solid, this is liquid membrane. And under solid membrane comes the isotropic or symmetric membrane. That means in every direction the membrane design is symmetric and uniform pore is there. That means the diameter of the pore is same in the in membrane in all directions. And second one is the anisotropic. Anisotropic membrane means the different structure is there. So uniform pore and this is the different side. and inside the liquid membrane comes the supported membrane. So liquid membrane needs to be supported somehow. So liquid membrane, when it is filled with pores, it is called the supported membrane, and another one is the unsupported membrane. Okay, so these are the basic classification of membrane. What is the pore size of ultrafiltration membrane? What is the pore size of ultrafiltration membrane? Yes.
0.1 micrometer to
Yes. So
5 nanometer.
the answer is 0.1 micrometer to 5 nanometer is the ultrafiltration size. Next, small organics are separated in nanofiltration. Small organics are separated in nanofiltration. Is it true? This is true. This is false, sorry. Yes, yes.
False.
Small organics are cleared through reverse osmosis, right? Small organics are
False.
separated through reverse osmosis. Next, what is the driving force of electrodialysis? Yes, this is electric field gradient.
Electric field gradient.
Next, write the differences between electrodialysis and dialysis. So, electrodialysis works on electric field gradient, and only dialysis works on concentration gradient. So we'll see the difference here. So this is the electrolyte solution where positive and negative charges are there. Now they are connected between cathode and anode, and voltage is given. So when the cation will go to the cathode and anion will go to the anode, electrodes attract ions of opposite charge. Now we are separating this with positive, alternative positive and negative charge serially. So this is the feed solution. And anion selective membrane do not let pass the positively charged ions. So the positively charged ions will be attached with the negatively charged plate, right? So you can see that how they are getting attached. And opposite is happening to the negative. The cation selective membranes do not let pass the negatively charged ions, so they are retained there. So now you can see that negative ions are in the left side, positive ions are on the right side. They are stored. And in the middle, there is the dilute we are using. The remaining concentrate can be used for further conversion. So this is how electrodialysis works. Depending on the electric field gradient or charge difference, potential difference, the particles are separated from a solution. Next one is the dialysis. Dialysis happen in human body. So that is how it is described. So the kidneys are the main organs. Dialysis happens in kidney. So why dialysis needs to be done? So kidneys are the main organs and osmoregulation and excretion happens through this. If they fail to function, the water content of our body cannot be regulated and metabolic waste will build up in the body. This may cause death. So we need dialysis. Our kidney machine can help patients with kidney failure to remove metabolic waste from their body. So how is it working? So you can see that fresh dialysis fluid. This is a constant temperature bath and in the right side this is from the constant temperature bath. This is going through pump into the body and from the other side used dialyzing fluid is coming out. That is the waste. That is tubing. This is the dialysis tubing. So from pump blood is coming. So here you can see this is the dialyzing fluid and blood is inside the tube. Differentially permeable. It only allows the small molecules such as urea and glucose but not large molecules like blood cells, plasma, protein or glucose to pass through. So blood cells will not be coming out, but all the small molecules like urea, they are coming outside into the dialyzing fluid through the differentially permeable membrane. The dialyzing fluid has the same concentration as normal plasma but has no metabolic waste. Therefore, urea diffuses from the blood to the dialyzing fluid down the concentration gradient. So because of the concentration difference, this urea is coming out, while glucose and other useful substances are retained in the blood because their size is also bigger and there is not concentration difference for concentration difference is only for the urea. That is how the metabolic wastes are removed from the blood using dialysis. This is how it is dependent on the concentration gradient and electrodialysis works on the electric field gradient. Next, how emulsion is separated from solution. How emulsion is separated from solution. Yes, it is ultrafiltration. Next, the pore size of dialysis membrane is less than 1 nanometer. The pore size of the dialysis membrane. Yes. It mainly works for the less than 5 nanometer. Yes, less than 1 is
False.
for reverse osmosis. Next is what are the materials used for filtration membrane?
Reverse osmosis.
What are the main materials used for filtration membrane? Yes, ceramics are used in ceramics are used nowadays. Then
Ceramics.
commercially available PVDF, that is polyvinyl, polyvinylidene fluoride, polyacrylonitrile, polypropylene, polysulfones, etc. Okay, so these are all different types of materials used for filtration membrane. Different type of filtration membrane. RO membrane is made of what? RO membrane is made of what? No, RO membranes are often made of polyamide. So polyamide is the.
Polyacrylonitrile.
What are the operating pressure for separation of different membranes?
Poly.
So for microfiltration, what was the operating pressure? So the pressure gradient is used for the separation process in case of microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. So what was those pressure? So for microfiltration, the pressure is below 2 bar. For ultrafiltration, the pressure is between 1 to 10 bar. For nanofiltration, the pressure is between 5 to 35 bar. And for reverse osmosis, it is 10 to 70 bar. That means how much small particle size they are handling, the pressure or pressure difference is increasing. So separate pressure driven processes now we will see. So first one is the microfiltration. So this is the microfilter filter membranes are used here. So this is the racks of vessels with each vessel containing thousands of hollow fibers. The outer wall of each fiber is made up of tiny pores, only 0.4 microns in size. So these pore size of the fibers are in micro region. That is why it is called microfiltration. So you can see that how the clear water is passing through the particles such as sleep, protozoa, yeast, bacteria, even viruses. Microfiltration processes are backwashed every 30 minutes to remove any buildup of particles on the membrane wall. The backwashed water is returned to the pretreatment tank for reprocessing. So, this is the microfiltration. The pore size of the filter is in the range of microns. Next one is the ultrafiltration. These are the different parts of an ultrafiltration chamber. The polyurethane coating, modified PVDF coated chamber. This is the hollow fibers used in microfiltration. So you can see the efficient image of this. The high capacity of contaminant retention happens. So it is a comparison of mechanical and chemical resistance of different materials. So you can see that 30 nanometer particles are separated. So here the feed is going. You can see that how they are clean. Now the clean water is available through the permeate section. This is for backward system. This is how the ultrafiltration chambers are cleaned. So sometimes it is cleaned through some chemicals also to enhance the backwash. So this is how they are done. These are the advantages of ultrafiltration membrane. Next one is the nanofiltration. So you can see here, this is a nanofiltration chamber. In which cases they are used in the industry, that is shown. This is the example. This is nanofiltration. That means the pore size here could be in nanometers. Next one is the reverse osmosis. So in case of reverse osmosis, what happens in osmosis? The opposite things happen. In osmosis, we will learn later that in osmosis, the solvent is going from higher concentration zone to lower concentration zone to higher concentration zone, right? But in case of reverse osmosis, the opposite happens. So these are the different layers of the RO membrane. is the seed channel spacer. Feed water is coming from there. High pressure into vessel travels small molecules like water pass through the membrane while larger particles such as salt, bacteria and viruses do not. The final recycled water product is collected from the end of the element. The concentrate or reject from that vessel flows to another stage, producing more recycled water. So this is the industry scale. Now we see what is the difference between nanofiltration and reverse osmosis. So in case of reverse osmosis, this the membrane sizes are different in case of reverse osmosis and membranes, nanofiltration membrane. So, and from unfiltered water to filtered water, different types of impurities are there, which are retented in case of RO membrane and which are not retented in case of nanofilter membrane. Next. When only water vapor can pass through a hydrophobic membrane, what is the name of the process? When only water vapor can pass through a hydrophobic membrane, what is the name of the process? The process is called thermally driven membrane process. So, thermally driven membrane process because near the membrane there is the thermal material is there, due to which the water becomes in vapor phase. The water converts into vapor phase, and that is how they are separated. But the other things which cannot be converted into vapor so easily, they are retained. So that is how this is separated. So the process is called thermally driven membrane process. In which separation process downstream is kept at vacuum state? In which separation process downstream is kept at vacuum state? The answer is pervaporation. Yes, pervaporation. In case of pervaporation, it also separates liquid mixtures. Microfiltration, ultrafiltration, reverse osmosis separates one solid particles and one liquid or one gas. But here, pervaporation separates two liquid mixtures, wherein the upstream of it is in contact with feed liquids and the downstream is kept in vacuum state. So, what is pervaporation? Let's see the video. So, pervaporation is where permeation, a combination of permeation and evaporation. So, transport and evaporation. We selectively evaporate substances through a membrane. So, water is such a case, one of such a case. Size of the molecules passing through the pores or on affinity with the membrane. The prime common denominators are sustainable technology and circularity. Yes, just a minute. So evaporation was not there till the microfiltration and reverse osmosis nanofiltration cases. But in here, it is the permeation and evaporation both are required.
Solve that.
So this is the industry use of the pervaporation. Okay. So which question? Yes. So second question is easy, I think, but still I'm doing.
Second.
So the question is, calculate the solute concentration in the membrane permeate site with a retentate concentration with a rejection coefficient of 0.6. So there is a in the membrane, if you notice, so in the membrane, if you notice, suppose that is a RO membrane. So when the some solution is coming, something is retented on this side. So this is the retented portion, and some passes through it. This is the permeate portion, and some things are getting rejected. That is rejected portion. So here in this question, it is given the question it is given that the rejection and permeation has a relation. Rejection, permeation, retention has a relation. So rejection is R, retentate, concentration retentate, and This is the permeation and this is again the retention. So this is the ratio of the retention, difference between retention and permeation, and divided by retention is our rejection. So that is what it is asked. So in the question it is said that the permeate membrane permeate site solute concentration in permeate site, it needs to be calculated. What is given the retented concentration and the rejection is given. So R is given as 0.6 and retented concentration is given as 0.4 gram per liter. So this is 0.6, CR is 0.4 minus CP by CR is again 0.4. So if you calculate what will happen, this is 0.24 equals to 0.4 minus CP. So CP is coming as 0.4 minus 0.24 equals to 0.16. Right?
Yes.
Rejection coefficient, where it is? 50 upon C. Rejection coefficient. Okay, it is rejection coefficient.
Okay.
Just a minute.
Then rejection coefficient is defined as sigma equal to 1 minus Cp upon C.
Yes. That is also that will also happen. Where is this? Is it in the lecture? Just a minute.
Sigma is given
Fine.
and concentration C is equal to 0.4 and
Yes, sigma equals to
calculate
1
the
minus
Cp.
Cp. That is also what? Sigma equals to 1 minus Cp by C.
Okay, ma'am.
Sigma is 0.6. 1 minus C is Cp is, needs to be calculated. C is 0.4, right? So how much is it coming? So Cp minus 0.4 is 1 minus 0.6, that is 0.4. Oh, it is coming 0.616 only. Yes, so both way it is corrected. Yeah.
Okay. Oh, yes.
Yes. What? Yes, yes. Both are same only, just
Okay,
written in a
okay.
different way.
Yes, yes. Okay, thank you.
Anything else?
Both are formula calculated in Cp. बहुत
Second one.
दोनों
Yeah.
फार्मूले से कैलकुलेट कर सकते हैं.
So it is also what? It aqueous slurry
Thank you.
solution has a concentration of 15
Okay.
gram per liter, which is filtered for 30 minutes with an operating
Question
pressure of 100 kPa. That forms specific cake resistance of 5 × 10 to the power 11
second last
meter per kg. The filter area would be 0.5. Calculate the volume of clear filtrate which can be filtered using the filter. Consider the viscosity of the filter as 0.002 and assume the filter resistance is negligible. So it will come to this problem where we are calculating the volumetric flow rate of the where we are calculating the cake resistance and the medium resistance formula. So what is that formula? So here yes, yes, this one mu C alpha divided by 2a squared delta p. So this portion is for cake resistance. From here we are calculating the cake resistance, that is Rn, and from here we are
Q equal
calculating
to
the alpha,
Qn
that is
upon
the
pi d square
this
upon
is the
4.
cake medium resistance, and this is the cake filter resistance. So this formula we'll use here also. So it is the question, it is itself said that the filter resistance is negligible. That means medium, this resistance is negligible. Membrane resistance or filter resistance is negligible. That means we can neglect this portion. So this is 0. Okay. So now from the opposite, from the rest of the, we can write it like this: T by V square mu equals to mu C alpha 2a square delta P, right? So now everything is given. So T is given as 30 minutes, right? So T will be 30 minutes means 30 into 60 seconds. Okay. Then, yes, then V square needs to be V needs to be calculated, right? V is the volume of the field fluid, it needs to be calculated. Then the solution concentration is 15 gram per liter. Solution concentration is C. C is 15 gram per liter, so we can convert it 15 kg per meter cube. This is same. So from gram to kg also it is, we have to multiply with 10 to the power minus 3, and from liter to meter cube also we have to multiply it with 10 to the power minus 3. So both will be cancelled out. That means it is the gram per liter is equivalent to kg per meter cube. We are converting the unit, otherwise we cannot solve. Then what is given? The pressure is 100 kPa. So the delta P is here 100 kPa. That is 100 into 10 cube Pascal. Next one is the what is given? The cake resistance. Cake resistance is the alpha. Cake resistance is the alpha. This is what value is 5 into 10 to the power 11. 5 into 10 to the power 11 meter per kg. And finally the area is, filter area is, A is 0.5 meters square. And there is another thing left, which is the viscosity of the filtrate is 0.002. Viscosity is 0.002 Newton second per meter square. Now if we put all the things we know except the V, we can calculate it. So what is the equation? It will be V square equals to T by mu C alpha, T by mu C alpha, and will be 2a square delta P. It will be 2a square delta P. So this will be our equation. So now if you put the values, 2 into T is 30 into 60, a square is 0.5 whole square, delta P is 100 into 10 cube, mu is 0.002, C is 15, and alpha is 5 into 10 to the power 11. So now if you calculate it, what will come in? How much this coming? So this coming as 6 into 10 to the power minus 3. So now we need V. B will be root over of this. Root over it will be 0.077 meter cube. So if you check, is it there? Yes. So it will be 0.077 meter cube.
Okay. I calculate.
Okay. Did you get it? Yes. Tell. Yes.
Okay, ma'am. Um, question number
So what is
6,
it
I
given?
am
It is
calculate.
said that
Please check.
the permeability needs to be calculated. The permeability having the
K
flux
is given and
0.5
calculate the
and with
F.
pressure at the feed side is
My answer
4.5
is
and
0
permeate side is 1.
0.01360
Newton per 5. So I think
0544.
first we need to
So
calculate the
then
pressure
calculate
drop.
answer
So
0.1 in 10
first
to the power minus 5 kg per
the
meter square
formula,
second fast.
yes, permeability is F by delta P, right? Delta P, so feed side is 4.5 into 10 to the power 5 minus 1 into 10 to the power 5, right? Yes. No, no, it is written like this way, so you are confused. It is 10 to the power 5.
P1
So it is coming as 3.5 into 10 to the power 5 kPa,
P.
right?
Yes, yes.
kPa or PA? It is PA. It is Pascal. Huh. Now, if we calculate
Yes.
the permeability, it will be the
And 10 to
flux
the
is
power 5.
0.5. Flux is
Only
0.5 and
4.5
it is
into
3.5 into
105.
10 to the
Sorry.
power 5.
Power.
So it is coming. It is coming 0.14, right? 0. So this is first one. 0.14 into 10 to the power minus 5. This is the permeability. Okay. So this is the answer. Yes.
Minus
So
5.
next question. When this is done, I think thermal giving memory process. This is the permeability.
Okay, thank you.
What is the working pressure of electrodialysis? What is the working pressure of electrodialysis? It is 1.01 bar. 1.01 bar. Next, what type of configuration is used in RO separation membrane? What type of configuration is used in RO separation membrane? Yes, RO, yes, tubular, spiral wound and hollow fiber. So now we will be seeing the different types of membrane configuration. First is the tubular. So in case of tubular, the thing is all rectangular and primarily used in micro and ultrafiltration applications. Here the
Tubular,
membranes are placed inside a support porous tube
tubular
and these
spiral,
tubes are placed together in a cylindrical shell to form the unit module. So here you can see that this is the rectangular shaped membrane support and inside it there is a porous one. This is the feed is coming and particles are retained and the other thing is which needs to be separated is permeated through the permeable membrane. This is the back pulsing. So whatever is happening is through the rectangular shaped chamber. Next one is the hollow fiber membrane. This is the hollow fiber membrane and is the clarification and disinfection of any type or quality of water in one single step. So thousands of hollow fibers are formed. It is mainly used in ultrafiltration. This is the barrier against suspended solids and microorganisms including bacteria and viruses. The high filtration capacity can sustain stability of the fiber the result of a fouling resistant hydraulic polymers of which it is composed. Filtration is carried out in an outside-in dead-end mode. Modules are thus compact and simple with optimized filtration surfaces without risk of fiber blockages. Backwashing can also happen so that the fibers can be cleaned. This is the hollow fiber membrane used in case of ultrafiltration. This is the membrane plates. So this is the membrane plate. This is the filtering cloth that is covering the plate. Now when the slurry inlet, this is the slurry inlet, chambers are filled, compact cakes and the filters, the dust particles which needs to be separated are clogged inside and the clear water is coming out, filtered outlet. This is a filtered outlet. This is a residual cake is here. So it should be cleaned with water, blow or air blow. And the cakes which are inside portion that also needs to be cleaned. This is for the washing purpose. So you can see how these cakes are removed now. With air and as well as water, both of them are used for layering. So now you can see that opening and discharge. So these are the cakes are discharged, which are removed. This is the plate type membrane. Next one is the flat sheet, ceramic flat sheet membranes. So it is look like the membrane surfaces look like this proprietary nano coated membrane, and the pore size of this is 200 nanometer. So this is the filter module. Area is defined. So this is filtration tower and rack. Submerged. What water or wastewater is filled in the basin. Vacuum driven systems brings water through the membrane into the filtered water channel. This is the filtered water channel and nano coated active layer. A cake layer of solids is formed on the outside of the membrane sheet. In between there is the permeate channel. And when cleaning is required, the flow is reversed. The unwanted material is then pushed off the membrane surface. You can see that inside out backwash method, these cakes are removed. So this is the flat sheet membrane. The last one is the spiral wool membrane. Separated into the feed is separated into two streams. So you can see this is the feed is coming where the particles and fluids are mixed, and after the when they are going out, you can see that permeate are the remaining components and the concentration of the particles are separated the level. So in cross flow filtration, the feed flows across the membrane element. Size of the membrane pore determine which modules are written and which are passing through. So this is the membrane surface. So you can see that liquids are separated here. The part of the feed that passes through the membrane surface is now called the permeate. Permeate spacer leads to the permeate into the permeate setup. So you can see the membrane element is made by several membranes and connected with different permeate tubes. So this is how a spiral wool membrane works. Next. difference between the dead end and cross flow filtration. So what are those? So in case of dead end, what happens? So all the feed applied to the membrane passes through it, obtaining a permeate. Since there is no concentrate stream, all the particles are retained in the membrane. Raw feed water is sometimes used to flush the accumulated material from the membrane. So that means the particles which are separated, they call the permeate, and the rest of the particles which cannot pass through the membrane are retained. That is the dead end filtration. And in case of cross flow filtration, what will happen? Here the feed water is pumped with a cross flow tangential to the membrane. That means feed is coming in the another direction, and the water is pumped in from tangential direction or perpendicular direction. This model implies that for a flow of feed water across the membrane, only a fraction is converted to permeate product as recovered. So first we'll see the dead end. So this one is the horizontal dead end ultrafiltration pressure vessel. So here you can see that feed is passing through and the particle that are retained is separated from the permeate. When clear water is coming in the permeate. This is the dead end. Next is the cross flow filtration. So feed is coming from here, which is different as normal dead end filtration. So feed is coming from the opposite side and water is coming from the other side. So here small molecular weight will pass through, which is called the permeation stream. This is the permeation stream. The suspended solid like bacteria, oil, some micron particles and dissolved components will be rejected. This is the retentive. So again, if we see, we will cross flow. So you can see that feeds are coming in another direction and the water is coming from the tangential way. This is a suspended solid membrane layer, and from the bottom the permeation is happening. You can see the feed tray, retentate and permeate. So this is the process. Next, what are the key elements in membrane separation process? What are the key elements in membrane separation process? So the first one is the membrane permeability. Membrane permeability is one of the important things of membrane in separation process. Second one is the operational driving force. Operational driving force per unit membrane area. Per unit membrane area. The third one is the fouling and subsequent thinning of the membrane surface. So these three things are the key elements in choice of the membrane separation process. Next is what is the general membrane equation for pure solvent like water? What is the general membrane equation for pure solvent like water? The general equation is for flux. In case of any case, it is the pressure difference. Delta P minus delta pi divided by mu into Rm plus Rc. So J is the membrane flux expressed as volumetric rate per unit area. Delta P is the pressure difference across the membrane. Delta pi is the difference in
dPc upon
osmotic
dS
pressure
1
across the membrane. Mu
micrometer
is the
1 minus
viscosity.
epsilon
And
gas
Rm is the membrane
upon
resistance, and
pi
Rc
s
is the
dP whole square
resistance
into
of the
epsilon
layers
c.
deposited. That is the cake resistance. And if pure solvent is there, like water, so in case of pure solvent, there won't be any osmotic pressure. So delta pi will be 0, as well as that because it is a pure solvent water, there is no solute which will deposit on the cake filter. So that is why Rc is also 0. So it will be lead to J into delta P by mu Rm. So for general equation, membrane equation for pressure driven membrane separation is delta P by mu Rm in case of pure solvent or any pure liquid. Next is what are the different types of build up that lead to membrane fouling? What are the different types of build up that lead to membrane fouling? So when membrane fouling happens, so if we one uses one type of filter membrane repeatedly without cleaning, the cake will be stored layer by layer, and it will reduce its efficiency. So fouling are related to the increased deposition of solid material onto the membrane surface, right? So it is the feed water on the membrane which causes a resistance to flow. And obviously, if the cake is very cake has very high thickness on the filter, then the pore will be inadequate and inefficient to clear the coming feed, right? So first one is the pore narrowing. What happens? First one is the pore narrowing. That means so much cake is deposited on the filter that the pore size becomes narrow. That the pore size becomes narrow from the original one. Second one is the pore blocking. Similarly, it completely blocks the pore. That means no fluid can pass through, no solution can pass through the filter anymore. And that happens when the particles of the feed water become stuck in the pores of the membrane. This is the second one. And the third one is the gel or cake layer. So layer by layer, just I have said that this type of formation takes place when the solid matter in the feed is larger than the pore size. So that means it is not it cannot permeate through the membrane. It is retented and it is forming a layer by layer deposition on the membrane, and that leads to fouling. So these are three main reasons for membrane fouling. Next one is the complete rejection from a membrane means rejection coefficient is 0. Is it true or false? So, if we notice the rejection coefficient, that is sigma equals to 1 minus Cp by C. So, complete rejection means rejection coefficient is 0. This is wrong. That is, this is false. Complete rejection means that, yes, that means Cp is 0. No permeate is there. No permeate is, when no permeate is there, that means nothing is passing through the membrane. Nothing can pass through our membrane. Everything goes into the rejection. So when that means Cp is 0, that brings us to the sigma equals to 1. And the opposite one, if everything passes through the membrane, if the whole feed solution passes through the membrane, that means Cp and C will be same, right? Cp and C will be same. That means in that case Cp and C will be same. So it will lead to 1 minus 1. That means sigma will be 0. So complete rejection from a membrane means rejection coefficient is 1. Rejection coefficient is 1. And when everything passes through the membrane, that means rejection coefficient is 0. So in this case, it is false. Next, in the filtration, flow resistances increase with time as the filter medium becomes clogged or filter cake builds up. So that is clear from the fouling itself, that when the filter medium becomes clogged due to repeated deposition of the dust particles or solid particles, that is narrowing the pore size or somewhere blocking the pores. That means when next flow is coming, it will experience more resistance from the filter membrane. So filter resistance increases. So filter resistance increases with time as filter medium becomes clogged. So the answer is true. Next question. As the time passes during filtration, either the flow rate or pressure drop. Which one is correct? What happens to the flow rate and pressure drop? So this is similar to the previous question. As the time passes during filtration, the flow rate, obviously due to the clogging, the flow rate will diminish and the pressure drop across the membrane bed will increase. This diminishes and rises. Flow rate diminishes and pressure drop rises. This is the answer. Next. Derive specific cake resistance. derive specific cake resistance. So if you remember the pressure pressure drop across a bed in yes. So when we have studied previously in case of laminar flow, the press in a packed bed, the pressure drop across the bed following the Koizumi-Kármán equation is 150 mu u 1 minus epsilon square divided by pi s dp whole square by epsilon q. Or
Then
if we
can
write
may I do so?
pi equals to pi s equals to Sp by Vp divided by 6 by dP. This is the sphericity formula, you remember, right? This is the sphericity formula. So if we include this here, so this equation will change into 4.17 mu u 1 minus epsilon square Sp by Vp square divided by epsilon q. So this is the, if the fluid is flowing as laminar flow through the membrane or cake, through the cake filter membrane, the pressure drop across the bed is defined by the Koizumi-Kármán equation. This one is the Koizumi-Kármán equation. We have solved it earlier in earlier lecture, right? Now you know the everything. Mu is the viscosity of the fluid, u is the velocity of the filtrate, then epsilon is the porosity of the cake, Sp and Vp is the surface area and volume of the single particles respectively, right? dPc is the pressure difference across the cake, and L is the length of the cake thickness, thickness of the cake. So now what is u? U is the linear velocity, I have said, right? So it is just simply you can write is dV dt by A. That means volumetric flow rate per unit area. V is the volume of the filtrate, A is the cross-sectional area of the filter medium, and L is the cake thickness, right? So this is the velocity of the filtrate. And similarly, if we want to know how this volume is coming of the filtrate, we can write it at A dl 1 minus epsilon, right? This is the volume of the filtrate. Now, if we multiply this volume of the filtrate, with if we multiply this volume of the filtrate with density, it will lead to the mass of the filtrate, right? So it will be A dl 1 minus epsilon into, this is the mass of the filtrate. Now, If we put these values in the pressure drop, that is dPc by dL, what will it be? So we are writing 4.17. We are writing 4.17, this 4.17 as a constant, which is K1, suppose, which is K1. Then mu is there as it is, U is there as it is. Okay. Then there is 1 minus epsilon. We are writing 1 minus 1 of 1 minus epsilon, and so we are not, this is we are taking dPc only. So dPc if we are taking, so there is dL is there, another 1 minus epsilon is there, right? And we are dividing, so we want to fix dm. So how we will fix dm in this equation? So in the bottom as it is, epsilon cube is there. So we have to multiply with A. Both of the things we have to multiply it with A and rho. So now if you remember, this is your nothing but dm, right? So now dPc, this pressure difference across the cake is K1 mu u 1 minus epsilon divided by rho A epsilon cube into dm, right? Oh, there is Sp plus Vp square, I forgot. Sp by Vp square. It is always. So now if we integrate the whole situation across the pressure drop and across the mass, it will be Pc delta Pc equals to K1 mu u Sp by Vp square 1 minus epsilon into Mc, which is divided by rho A epsilon cube. Okay. And now we can rearrange it. So if we rearrange it in such a way, that is delta Pc A divided by mu u Mc is in the left hand side, and what is left is would be the right hand side. Right hand side is there K1 Sp by Vp square 1 minus epsilon divided by rho P and epsilon Q. Now this is called the cake, specific cake resistance. Specific cake resistance, that is alpha. So alpha will be K1 Sp by Vp square 1 minus epsilon and rho epsilon cube, as we are defining alpha as delta PCA mu u Mc, right? So this is the derivation of specific cake resistance. Next, for incompressible cake, specific cake resistance is independent of what? For incompressible cake, specific cake resistance is independent of what? So for specific cake resistance, for incompressible cake, specific cake resistance is independent of pressure drop and position of the cake. Okay. So for incompressible cake, specific cake resistance is independent of pressure drop and position of the cake. Next. So next is coming, that is filter medium resistance is proportional to pressure drop across the filter bed. Filter medium resistance is proportional to pressure drop across the filter bed. Is it true or false? So if you notice the formula of filter medium resistance, that is nothing but delta Pm by mu U. So obviously Rm is proportional to delta Pm. So this is true. Next, how to calculate the filtered cake and filter medium resistance. So it will come from this only. So previously we have seen the delta Pc, right? So specific cake resistance is alpha equals to delta Pc A by mu U mc. So now if we write delta Pc is mu U mc alpha divided by A, and delta Pm, that is what coming from this one, Rm, delta Rm equals to delta Pm by mu U. So delta Pm is delta Rm into mu U, right? So now the total pressure drop across the filter bed, that is delta P, is summation of these two, delta Pc plus delta Pm. So if we sum up these two, what will be? So mu U will be common. It will lead to mc alpha by A plus Rm, right? So now, what we know? mc is the total mass, right? mc is the total mass, means the volumetric flow rate of the cake, volumetric flow rate of the filtrate, and c is the or not flow rate, volume of the whole filter cake, and c is the mass of the particle deposited in the filter per volume of the filter, right? This is c. C has another expression which is defined as C equals to Cf divided by 1 minus Mf by Mc minus 1 into Cs by rho P. So here this is not important, just to know the everything I am telling. Mf is the mass of the wet cake, Mc is the mass of the dry cake. Cf is the concentration of solids in the slurry fed to the filter, and Cs is the concentration of the slurry, which is equal to Cf, and rho is the density of the not rho p. Rho is the density of the liquid. Previously, in this case, what rho we are using, that is rho of the particle, that is rho p. So if you write as rho p, that will be easier to understand. Particle density. Now is the filtrate density. This only rho. So now, if we substitute the values, in this equation, so we know that is delta P equals to mu u mc into alpha by A plus Rm, right? So now we are putting the value of u. U is, previously we know u is volumetric flow rate per unit area. So it is mu u is dV dt into A, and mc is V into C into alpha by A plus Rn. So now from there we are separating dt dv. dt dv is equals to mu A delta P is coming here, and inside it will be as it is alpha CV by capital A plus Rn. Now if we integrate this, what we will get? We will get T by V, that is time by volume of the filtrate, equals to mu C alpha by A square into delta P. Mu C alpha by 2A square, right? So we are integrating with respect to V, right? So here there is a V, this is constant. This portion is the integrate. So if we integrate, so suppose you know the integration of V dV, right? This is V square by 2. So that is why this 2 is coming. A square delta P. This is V. Okay, I will show. So now we are integrating and we are separating first. So dt equals to mu C alpha by A square delta P into V plus Rn whole into dV. That is how we are integrating, right? So now when I am integrating complex, it will be T equals to mu C alpha by V square by 2, that is 2A square delta P plus that is mu also, right? Mu A delta P. Yes, here it is mu Rm A delta P. Is already there, right? So this is constant, nothing will happen to this. It will be So integrating from this is V square, this is mu Rm by A delta P into V, right? This is just a constant. So now we are taking out the V. So T by V will be mu C alpha 2A square delta P V plus mu Rn by A delta P. Now if we simplify this equation, we will write as P by V equals to AV plus B. And here A is the mu C alpha by 2A square delta P and B is mu Rm by A delta P, right? So this is a straight line equation, right? Y equals to mx plus c, where m is the slope of the straight line and c is the intercept of the straight line. So here A is the slope. From here we are calculating our alpha, that is cake resistance, and from the intercept we can calculating the filter cake and filter medium resistance. Okay. Next question. Rotary vacuum filter operates at constant pressure. So rotary vacuum filter operates at constant pressure. Okay. If filtrate flow rate increases, what will increase from the following options in case of rotary drum filter? If filtrate flow rate increases, what will increase from the following options? So, filtrate flow rate of rotary drum filter expression is QF equals to 2A square delta P FSN divided by mu C alpha to the power half, right? So if filtrate flow rate increases, if QF increases, what will increase from the following option? If QF increases, A will increase, delta P will increase, Fs will increase, N will increase. So drum speed is N, right? So option. Otherwise viscosity will be decreased because it is in denominator. Concentration of the cake solids, the C and cake resistance alpha all are in denominator. So that will decrease if flow rate increases, right? So it will be drum speed. Next, difference between osmosis and reverse osmosis. We see little videos. So this is your osmosis. Okay. So basically osmosis in layman language, it is when solvent is flowing from low concentration zone to higher concentration zone, that is the osmosis. When the solute dissolves in the solvent, it makes a solution, right? So this is the membrane is there that separates two solutions. The solution on the right side is higher solute, that means highly concentrated, and solution in the left side is the lower solute, that means low concentrated. So now you can see that the solvent is going from lower concentration zone to higher concentration zone until it becomes equal. It comes into equilibrium. So this is the osmosis. Osmosis diffusion of water with semi-permeable or selectively permeable membrane such as the plasma membrane that surrounds cells during osmosis. Water diffuses down in concentration gradient. So you can see higher concentration zone to lower concentration zone. Okay. Where water is high, water will go from there. It will reach to the where solute concentration, if any other solute is there, where the solute concentration is high, it will go to that place. From higher to lower water concentration, just like other molecules or ions. You can also say that water moves from an area of lower solute concentration to an area of higher solute concentration. Sometimes this confuses people, but if you think about it, makes sense, right? So initially I have told that when you talking about from the point of view of solute concentration, osmosis is water will go from lower solute concentration region to higher solute concentration region. But if you talking about the water molecules, you have to tell that water molecule will go from higher water concentration zone to lower concentration zone. Okay. So you have to be very careful what you are writing or what you are saying. So this is the say solution. 1% solute is 99.9% water, but a solution with 20% solute is only 80% water. The higher the solute concentration, the lower the water concentration, obviously, and vice versa. So this is your osmosis. Water flows solute, if you can remember physically also, but we do use a few terms to describe relative solute concentrations, that is hypertonic, hypotonic, and yes. Higher in solute means hypertonic. Water will always flow from membrane towards the hypertonic solution. Okay, and this is the lower in solute means hypotonic. So this is the basic. This is the telling in details way. We don't need to go further. Next, we'll see the reverse osmosis. This is the opposite of the osmosis. This is just the opposite of the osmosis. Okay. So in this animation, we may look like erratic particles. Motion is really particles bouncing off the invisible front and back walls, right? The small red particles are able to pass through the holes in the membrane, whereas the large white particles are not able, right? You are seeing. Initially, there was only red particle in the left and white particle on the red. Each time the red particle is passing through the membrane and it goes into the chamber of the white particles. In equilibrium conditions, there will therefore be some red particles on both sides of the membrane, whereas the large white particles will always only be on the right side, right? You can see. This means that in an equilibrium condition, there will be a greater number of total particles on the right side of the membrane than on the left side. Or in a much easier way, you can see this video. What is reverse osmosis? Water molecule and virus, you can see. Up to 10 times larger. most chemical contaminants, and all microorganisms such as viruses and bacteria. Two streams of water are produced: pure clean water or permeate across the membrane sheets and passes through the membrane layers to the inside tube. Water that does not permeate becomes more highly concentrated with salts and other substances. This water is called concentrate. Water flows out the pore vessel and flows out another outlet. The concentrate water can then flow into the other. The reverse osmosis is how it is working. Water is flowing from the higher concentration zone to the lower concentration. In case of osmosis, it is happening in the opposite direction, right? Higher solute concentration and lower water concentration. This is the difference between osmosis and inverse osmosis. So in case of osmosis, you can see where the water is more. In the case of left, it will be water will pass through this membrane to the right side to reach the equilibrium. So you can see that water level is receding and it is entering into the salt water position. That is osmosis, right? This is your osmosis. And in case of reverse osmosis, it will be the opposite one. And now reverse osmosis. Now the pressure is giving on the opposite position, and water is coming from that position to that left position. And only the salt water and only the membrane is permeable to the water molecules, not the salt molecules. That is why this is how the impurities are separated with the help of reverse osmosis. So you can understand the difference, right? Next question. When delta P greater than delta pi, what happens? So when delta P greater than delta pi means the reverse osmosis happens. Oh my God, what happened? So what will happen? I can write it. Okay, I actually lost my pen. That is why. 1 minute, I got it. What will happen when delta P is greater than delta pi? You have seen, so delta P is greater than delta pi means the reverse osmosis happens. That is RO. That is water flows from the concentrated to the dilute salt solution side of the membrane, right? You have seen the video just and it will be easy to remember. Next question. The higher the recovery, the stronger the water production capacity of the RO system. The higher the recovery, the stronger is the production of the RO system. The answer is true. Next, what are the expressions of observed and real rejection? So, rejection, you know, observed rejection is feed concentration, then the permeate concentration divided by feed concentration. Hence, real rejection is the C delta 1, it is defined here. C delta 1 means the Solute concentration at the membrane surface. Solute concentration at the membrane surface, solute concentration at the membrane outlet divided by solute concentration at the membrane surface. So solute concentration at the membrane surface only means P delta 2 means Cp only, the permeate concentration. So P delta 1 minus Cp divided by C delta 1. This is the expression. Okay, that is for today. I hope you will find the lecture helpful. The question I have solved, you will find this helpful. And if you have any question, you can raise the question in the discussion forum. We'll meet on next Saturday. Till then, goodbye.